Now we're going to switch to a discussion of frames. First, some definitions. A multi-force member is a structure in which at least one member is acted upon by three or more forces at different angles. Frames contain multi-force members. They're designed to support large loads and are usually stationary. On the bottom, you see a picture of a house under construction where the wood frame up on the top is designed in a similar way as simple trusses. Usually you get a little more in the way of right-angled intersections than you see with the bridges, but the basic idea is the same. On the right, you see a metal frame for a piece of gym equipment where the frame members are welded in place at the corners, and the frame shapes don't have to be straight. They can be curved in space, such as these ones on the top, or they can be on an angle relative to the ground, as this back one and this back one are doing. But the basic idea is for the frame in gym equipment to be a series of welded heavy members that can support not only the weight of the other pieces on the equipment, but up to typically on the order of 500 to 600 pounds on a barbell for the very large people that inhabit the gym and are going to lift weights of that magnitude. The frame of figure 619A, which we briefly went over at the beginning of this chapter, is shown here again at the bottom, and it carries load W, and it's held in place by cable DG. DG keeps the frame from wanting to rotate due to the weight W. Weight W would make the frame rotate clockwise around pinned reaction point A, but the existence of the cable DG provides the counterclockwise moment to keep the frame stable. We can solve for T by summing the moments around point A. We can sum the x forces to 0 to find the force A sub x, and we can sum the y forces to 0 to find the force A sub y at point A. Figure 6.19c shows a free body diagram for the internal forces. Member BE is the only two force members. The other members AD and CE are multi-force members. AD has 5 forces in it, and CF has 4 forces in it. We call the forces on the ends B and E of member BE FBE and minus FBE. Member BE is assumed to be in compression. The forces on the midpoints at points B and E on the multi-force members are shown as equal and opposite to those on the ends of member BE. Joint C connects members AD and CF, and the reactions at C are C sub x and C sub y with the assumed direction shown. The magnitudes of the forces in member AD are C sub x and Cy, and thus the magnitude of the forces in member CF are minus Cx and minus Cy. We can sum the moments around point C and set that to 0 in member CF, and that will allow us to find F sub BE. And we can sum the moments around point E in member CF, and we can find C sub y. Once we know F sub BE, we can sum the forces in X equal to 0 in member CF to find C sub x. Here is a sample problem 6.4 in which we'll find the forces in all of the frame members in the picture at the bottom of the screen. Members ACE and BCD are connected by a pin at point C and by the link DE. We're going to determine the force in link DE and the components of the force exerted at point C on member BCD. In order to do that, we're going to first treat the entire frame as a free body and find the reactions at pinned point A and point B on rollers. Then we'll take apart the frame and we'll treat each of the members as its own free body, and then we'll use the equations of equilibrium to find the forces in member DE and the forces at point C. Here's a free body diagram of the entire frame with external forces 480 newtons. There are reactions AY and AX at point A, and only a horizontal reaction B at point B because point B is on rollers. We're going to sum the forces in the Y direction to find A sub Y, and there's only one other force in the Y direction, and that's 480 newtons pointed down, and therefore AY has to be 480 newtons pointed up. We're going to sum the moments around A to find force B. When we sum the moments around A, we see that the 480 newton force wants to rotate clockwise around point A at a perpendicular distance of 100 millimeters, and the force at point B wants to rotate counterclockwise around point A at a perpendicular distance of 160 millimeters. We put those in our equation for the moment, set it to 0, and find that B is shown in the correct direction with a force of 300 newtons. When we sum the x forces to 0, the only other x force besides B is A sub x, and because B is 300 newtons to the right, A sub x has to be 300 newtons to the left. In step 2, we take apart the frame. BCD and ACE are connected at point C, so C sub x and C sub y in these two members are equal and opposite, but with assumed directions. In member BCD, we show C sub y going up and CX to the right, and in member ACE, we show equal and opposite, CX goes to the left and CY goes down. We're also going to assume that FDE on member DE is in tension, which we show by having the arrows pull on that member. Now we calculate F sub DE, CX, and CY. First, we can sum the moments around point C in member BCD to find F sub DE. And to do that, we have to be able to break out force F sub DE into its horizontal and vertical components. The angle alpha between FDE and the vertical downward direction is calculated from the fact that we can create a triangle with a vertical height of 80 millimeters and a horizontal distance of 150 millimeters based on point D, point E, and the location where the 480 Newton force is applied. And then all we have to do is take the inverse tangent of 80 over 150 to find out that this angle alpha in the picture is 28.07 degrees. Then the downward force, F sub DE, is FDE magnitude times sine of the angle, and it has a lever arm of 250 millimeters away from point C, and that force, FDE sine alpha, wants to rotate counterclockwise around point C. And our second term in our moment equation comes from the 300 Newton force acting to the right, which has a lever arm of 60 millimeters, and it wants to rotate in a clockwise direction around point C. And our 480 Newton force wants to rotate counterclockwise around point C at a perpendicular distance of 100 millimeters. We then calculate that F sub DE is minus 561 newtons, and it's actually in the opposite direction of what we've drawn because of the negative sign. Now we sum the x forces to find CX. CX minus F sub DE times the cosine of alpha plus 300 newtons, which is going to the right, equals 0. And notice FDE in the picture is shown going to the left, so that creates one negative sign. But then we put in a minus 561 newtons for the second negative sign. You'll actually be adding the magnitude of FDE times cosine alpha in this equation. And we also have to add the 300 Newton force, which is clearly going to the right, equal to 0. And when we do that, we find that C sub x is actually minus 795 newtons, which means it was really going to the left after all, too. Then we sum the y forces in F equal to 0. We have plus C sub y for its assumed direction, minus FDE times the sine of 28.07 degrees. And again, we have two minus signs in this equation, which are going to cancel. Minus 480 newtons equal to 0. And when you solve for Cy in this equation, you find that Cy does have the correct assumed direction, and it has a magnitude of 216 newtons. In step 4, we check the calculations by summing the moments around point A equal to 0 in member ACE. Using FDE is minus 561 newtons, and CX equals minus 795 newtons, and CY equals plus 216 newtons. And we keep those signs from the prior step 3 because we're reversing the direction of CX and CY in this picture anyway, so you don't want to do a reversal of direction twice by changing the signs for CX and for CY. So when we sum the moments around point A, we get FDE times cosine alpha. FDE in its assumed direction is pointing up and to the right. FDE cosine alpha is pointing to the right. It wants to rotate counterclockwise around point A at a distance of 220 plus 80, which is 300 millimeters. When we plug in minus of 561 newtons times cosine alpha, we're going to effectively have a clockwise direction for the moment. And FDE times sine alpha is vertically up in the picture with the assumed direction, and it wants to rotate counterclockwise around point A. With the minus 561 Newton sine, though, you're going to find in this equation that it's going to effectively rotate clockwise that moment around point A. And then we have our minus CX. Here's CX. We get a minus sign in CX because of its current direction wanting to rotate clockwise around point A. But by the time you pump in a minus 795 newtons for CX, the effective rotational direction of the force is going to get switched to counterclockwise. Its lever arm is 220 millimeters, but the key message here is don't change the signs of the forces when you go from one member to the next. Leave them alone because you've already accounted for that by changing the directions of the arrow in ACE compared to what it was in its neighboring member, which was BCD. In sample problem 6.5, we're going to find the forces in all of the frame members shown in this picture on the lower left. But you won't be able to determine forces in one member without analyzing a second member at the same time. Members ABE, ACE, and BCD are connected by pins at points B and C. We're going to treat the entire frame as a free body and solve for the reactions at E and F, and then we'll take apart the frame and treat each member as a free body. And we will simultaneously analyze two of the members, ABE and BCD. First, we're going to find the reactions at points E and F. By summing the moments around point E and setting that to 0, we can find F. We have this minus 2400 Newton external force, which wants to act clockwise around point E at a perpendicular distance of 3.6 meters. Add that to force F, which wants to rotate counterclockwise around a point E times its perpendicular distance of 4.8 meters. Set that to 0, and you find that force F is 1,800 newtons and pointed up as shown in the diagram. When we sum the forces in the y direction and set that equal to 0, we've got F is plus 1,800 newtons up, a 2,400 newton force down, which means EY has to be 600 newtons going up in order to maintain equilibrium. EX equals 0 because there are no external horizontal forces. In step 2, we're going to take apart the frame. AX and AY are equal and opposite forces in members ABE and ACF. BX and BY are equal and opposite in members ABE and BCD, and forces CY and CX are equal and opposite in ACF and BCD. In member BCD, we're going to sum the moments around point B, set that to 0, and that will allow us to find C sub y. We have our minus 2,400 newton force. It's got its lever arm of 3.6 meters, and it's rotating clockwise around point B. We add to that a moment from force C sub y, rotating counterclockwise around B at a distance of 2.4 meters. C sub y equals 3,600 newtons, shown in the direction that we have in the diagram. We then can sum the moments around C, set that equal to 0 to find B sub y. Now we have our 2,400 newton force, and it's rotating around C in a clockwise direction, and it's at a distance of 1.2 meters. We add that to BY, which is rotating around point C in a counterclockwise direction at a distance of 2.4 meters. Set that to 0, and we find that BY equals 1,200 newtons, also shown in the direction that we have it in this diagram. When we sum the forces in X equal to 0, all we can conclude is that minus B sub X plus C sub X is equal to 0, and we can't get any further than that. Now in step 4, we're going to use member ABE and sum the moments around point A and set that to 0, and we'll use that to find B sub X. Now B sub X is the only force in this diagram which does not actually have its line of action going through point A. And therefore, B sub X times this lever arm of 2.7 meters equals 0, which means B sub X has to be 0. Now that we know B sub X is 0, A sub X has to be 0 because BX minus AX has to equal 0. In member BCD, we learned that minus BX plus CX equals 0. And now that we know BX is 0, that means CX is 0 too. When we sum the forces in Y and set that equals 0, we have minus AY plus BY plus 600 newtons equal to 0. We knew that BY was 1,200 newtons from calculations before, which means that AY has to be 1,800 newtons. In step 5, we will sum the moments around point C in member ACF and set that to 0. We'll then plug in values to verify that ACF is in equilibrium by showing that when you put the constants in, you really do get 0 in the equation. We have this 1,800 Newton force at point F, and it acts in a counterclockwise direction with a lever arm of 2.4 meters around point C. We have AY acting in a clockwise direction, so minus AY times its lever arm of 2.4 meters minus AX times its lever arm of 2.7 meters, but AX equals 0, so that term does not contribute. We then see that 1800 newtons times 2.4 meters minus 1800 newtons times 2.4 meters does indeed equal to 0, and we know that member ACF is in equilibrium. Let's take a look at frames that will collapse without their supports. For example, in figure 6.20a at the bottom, we have two members, AC and CB, which each carry loads P and Q at their midpoints. Member AC and CB are supported, respectively, by pins at A and B, and they're connected by a pin at C. But if we detach the frame ACB from its supports, these loads P and Q pointed downward would just take this pin and push point C down and flatten it such that member ACB would quickly be in a straight line flat down on the ground. Therefore, we conclude that the frame is not a rigid body. The equations of equilibrium, sigma f sub x equals 0, sigma f sub y equals 0, and summing moments equals 0, define equilibrium for a rigid body, but that doesn't apply to a non-rigid frame. If we want to do analysis, we need to take the frame apart and analyze members AC and CB individually to find the reactions at points A and B. AC and CB then become multi-force members. Each of them has 5 forces in it, and pins are at the supports and the connections. CX and CY are equal and opposite in the two members, as shown here at the top. And these internal forces at point C will cancel each other, so the equilibrium equations are also satisfied by the external forces P and Q, along with the reactions A and B. Now we're going to show you an example in problem 6.6 of finding external reaction forces in a frame iteratively. And just like in the example before, because supports E and F are both pinned, this frame is over-rigid and statically indeterminate, and it will collapse without the pins at points E and point F. This 600-pound force that's acting to the right at point A will just push the whole frame over on its side, and all the members will collapse into horizontal lines that will be parallel to the ground. We have a 600-pound horizontal force applied to pin A of the frame, and we're going to determine the forces acting on members ACE and BDF. We'll be able to partially analyze the frame, study the members, and then return to frame analysis to find the reactions at E and F. In the assembled frame, we sum the moments at point E and set that equal to 0, and we find F sub y, and we can sum the forces in the y direction to find E sub y. But further use of the equilibrium conditions are insufficient to determine Ex and F sub x. Summing the motions around point E, set that equal to 0. We have our 600-pound force acting clockwise in a moment around point E times a 10-foot lever arm. We then have F sub y, which will supply a moment that's counterclockwise times 6 feet, and we find that F sub y is 1,000 pounds. And because F sub y is 1,000 pounds, that means E sub y has to be minus 1,000 pounds. But if you try to sum the moments around F and set that to 0, all you will get is another equation for E sub y, and we already know E sub y. And if you try to sum the forces in X and set that to 0, all you'll get is that E sub x plus F sub x is equal to the 600 pounds, but of course that equation has 2 unknowns in it. So you won't be able to get either E sub x or F sub x. Therefore, we need to take apart the frame to go further. Force F sub AB is equal and opposite in member AB, in member ACE, and in member BDF. Force FCD, here's FCD, is equal and opposite in CD, ACE, and BDF. We're going to place the 600-pound force in member ACE because it'll make that analysis either. It could have gone in AB, but we have a lot of other forces in ACE already, so we want the external load to be there to ease up on our calculations. And we take a look at the geometry and we see that connecting points in A and B, we can make a right triangle where the actual dimensions are 2.5, 6, and 6.5. But we've got this notation here for a 5, 12, 13 triangle that we can use instead of having to figure out all the angles and use sines and cosines. And we'll use the 5, 12, 13 notation instead. Same as this triangle connecting D and point C and going horizontally and then up vertically in member BDF. In member ACE, we'll sum the y forces equal to 0, and we'll sum the moments around point E equals 0 to create two equations involving the unknowns F sub AB and F sub AC. Summing the y forces equal to 0, we have FAB pointed downwards multiplying by 5 over 13, as this again is a 5, 12, 13 triangle. And we have a plus 5/13, there's our 5, there's our 13, times an FCD, because that's pointed up. And we have minus 1,000 pounds. Set that equal to 0, and that's one equation. We sum the moments in point E equal to 0. And we have our 600-pound force going clockwise around point E, so it's a minus 600 times a lever arm of 10 feet, which is 7.5 plus 2.5. We have minus 12/13 times FAB. Here's FAB, and it wants to go in a clockwise direction around E, but its x component is 12/13 of FAB. And hence the minus sign because we're rotating clockwise, and its perpendicular distance is also 10 feet, 7.5 plus 2.5. And we have FCD is wanting to rotate clockwise around point E, and its horizontal component is 12 divided by 13, but its lever arm is only 2.5 feet, and that's our second equation. And when we solve these two simultaneous equations, we find that F sub AB is minus 1040 pounds. And so FAB is in compression at joint A. And F sub CD is plus 1560 pounds. Therefore, it's in tension at joint C. In step 4, we're going to sum the x forces equal to 0, and we can solve for E sub x. We know that 600 pounds is pointing to the right, so that's a positive. We take 12/13 of FAB, which is minus 1040, and we take 12/13 of FCD, which is plus 1560, and add that to EX. And solving that algebraic equation, we see that E sub x is minus 1080, so that it's really pointed to the left as opposed to what is in this diagram pointing to the right. Then we can return to our free body diagram of the entire frame and sum the forces in x to solve for F sub x, because we knew that 600 pounds plus EX plus FX equals 0, but EX equals minus 1080 pounds, which means that FX equals plus 480 pounds, and is in the direction as shown in figure 1. Then we can check the results by verifying that the equation summation m sub b equals 0 is satisfied in member BDF. We sum the moments around B, and we first take FCD, which is going clockwise around point DE when we take 12/13, meaning the horizontal component, and it's separated by 2.5 feet, and we plug in 1560 for FCD, plus F sub x, which wants to go counterclockwise around point B, and it has a perpendicular distance of 5 plus 2.5, which is 7.5 feet. And we look at that equation and we get minus 3600 plus 3600 equals 0, which means that the moments really are 0 around point B and that member BDF is in equilibrium. In the simplest definition, a machine is a structure that's designed to convert an input force to an output force. In figure 6.21a, we show a pair of cutting pliers, an example of a machine, and they're used to cut a wire by applying input forces on the handle, P and P minus, and the pliers exert output forces, Q and minus Q, on the wire. In a hydraulic lifting table, a hydraulic cylinder supplies the input force, and the output force lifts the table. The scissor jack, which I'm showing here, this whole scissor mechanism, transforms the input force from a linear motion going along the axis of the cylinder to an output force going vertically relative to the ground. And in a bicycle, your feet push on the pedals, which supply the input force. And the output force produces torque to the rear wheel. The front and rear gears, here's your front gears, behind this guy's foot's your rear gears, and that rear wheel are the mechanism that transform the input force of your feet pedaling to the output force, which provides torque to the rear wheel. And the output force, of course, what moves the bicycle forward. And of course, if this guy doesn't watch it, he's going to go forward too fast and go flying down that mountain. Sucks for him. A pair of pliers forms a non-rigid structure. And to determine output Q, when we know the input force P, and of course the input force P is coming from your hands, we draw the pliers showing P and P minus, and the reactions minus Q and Q that the wire exerts on the pliers. Then we use only one member of the pliers as a free body in order to determine the output force Q. We can sum the moments around point A to solve for Q. And we find that 0 equals P times A, so here's force P times lever arm A, minus Q, which creates a moment in the clockwise direction, times lever arm B. And thus Q then equals A over B times P. We can use the top member to determine force A. When we sum the x forces, we find that AX equals 0 because there are no external x forces, but summing the y forces, we find that AY going up is just the sum of P and Q going down, and that's just equal to 1 plus A over B times P. Here's an example of a very large cutting pliers cutting a gym locker. Some of you may have had that experience in high school. You put your lock in the gym and you forget the key or you forget the combination, and the gym supervisor comes along with his massive pair of pliers, gets to provide a very large input force, P, here where the hands are, and then the force Q is amplified even more because of that ratio 1 plus A over B times Q, where A relates to the length of the pliers. and these pliers are very long. So this very large output force on the hasp of the lock will shear it instantly, and then the lock gets opened and you get your stuff out of the gym locker. Here's some general notes about solving for forces in complex machines. First off, machines are always non-rigid because by definition they have moving parts. And before attempting to solve a problem, you must determine whether a structure is statically determinate or not. You usually have to use several free body diagrams to create simultaneous equations for the unknowns, and you should choose free body diagrams that can relate the output forces to the input forces. And make sure not to let the total number of unknown force components exceed your available number of independent equilibrium conditions. Here's an example problem 6.7 where we're going to find the forces exerted by the cylinders of a hydraulic lift. In this example, a hydraulic lift table, like the one in this lower right corner, is used to raise a 1,000-kilogram crate. And the table consists of the platform, so here's a side view of the platform, and here's the platform in the isometric view, and two identical linkages on which two hydraulic cylinders exert equal forces. Now my photo here only shows one hydraulic cylinder, but in our example, make believe there's one hydraulic cylinder on the left and one hydraulic cylinder on the right, which exert equal forces. And if we have two hydraulic cylinders, we can simplify the problem and use only one set of linkages, say this left set as opposed to the right set of linkages, and use that in the analysis so that the load will be half of W, meaning 1,000 kilograms divided by 2, or 500 kilograms lifted up by one cylinder. In the figure on the lower left, EDB and CG are each of length 2A. So here is EDB and here is CG, and they're of length 2A. And element AD, there's AD, is pinned to the midpoint of EDB. And the length of the lift from left to right is capital L. Point G here is located at the midpoint, L over 2. And we need to determine the force F sub dH exerted by each cylinder in raising the crate at the point when angle theta equals 60 degrees, little a equals 0.7 meters, and L equals 3.2 meters. Now in this problem, the lengths of L and A are constant, but this angle theta does vary depending on how far the table is lifted up. So we can only pick one point, theta equals 60 degrees in this particular problem, and determine force FDH, but in reality that force FDH is going to change as the table lifts up and up and up. We're going to show, however, that at least the result is independent of this distance d, where d is the distance from point A, and showing you in 3D, roughly by this yellow label, to the center of gravity of our massive crate that is sitting on top of the table. Here's an example of a commercial hydraulic lift cart with foot pump. And you can watch the video on YouTube of how this mechanism works. And here is another example. This one's a vertical double hydraulic cylinder lift table, and this one's got a remote control. And you can see the video here in YouTube and watch it go up and down and get a better feel for how these hydraulic tables work in practice. Back to our sample problem. The free body diagram of the entire frame involves more than 3 unknowns, and so we'll need to draw free body diagrams of each component of the machine and then solve for forces in each of them. The free body diagram of figure 1 in the lower right corner shows the platform and linkages, and it includes these forces. We have input force FDH, which comes from the hydraulic cylinder and acts at point D. There's point D. Half the crate weight 1/2 W is at a distance d from point A left to right, and the reactions at E and G are shown. Let's take a look at each member of this free body diagram. Member CG is in compression. We're showing the forces acting at C and G individually, and we know that's true because CG is directly bearing a lot of the force of this massive crate. Its force is going to be pushing down and squashing this linkage. So it's pretty obvious that CG is in compression, and therefore the way we're drawing the arrows is not really an assumption. It's the way that the linkage really is. And we assume, though, that AD, here's AD, and BC, and here's BC, are in tension, but we're not really sure yet. We're just assuming that. F sub BC on member CB, here's F sub BC, left and right, in tension, is equal and opposite to F sub BC, which is drawn on member EDB. So here's F sub BC. And it's also equal and opposite to F sub BC, which is acting at point C. F sub AD, which is on member AD, assumed again to be in tension, is equal and opposite to this force F sub AD on member EDB. And it's also equal and opposite to force F sub AD, which is acting on roller A. And F sub CG on member CG, which is shown here, that one is equal and opposite to F sub CG on roller C. We can sum forces in the x direction on our platform and quickly find that F sub AD is 0 because there are no external horizontal forces. And when we sum the y forces and set it to 0, we get an equation that relates forces B and C. B and C point up, and they have to be equal to this 1/2 W force of the crate that is acting down. We can also make a force triangle for roller C, where we show the angle theta, which is 60 degrees, and we've got force FCG acting up and force C goes down on point C, and F sub BC acts to the left. And from this force triangle, we create a relationship between force F sub BC and force C that says that F sub BC is equal to C times a cotangent of theta, where theta is 60 degrees. Then we can sum the moments around point E and set that to 0 to find the second equation relating forces B and C. And to do this, we take link EDB and we focus just on the bottom half here between E and D, and that distance from point E to D is small a. This linkage is angled at angle theta equal to 60 degrees relative to the horizontal, and this angle phi is the angle between the linkage EDB and the force FDH. And to understand the geometry further, I drew a triangle showing the angle theta and of length A between point E, point D, and I also drew a complementary triangle up here at the end where force F sub DH is here on the line. Angle phi is the angle between FDH, swept angle over here to the edge of the linkage. There's phi. And then because this angle here at the bottom is a 90-degree angle, this angle up at the top is phi minus 90, which means in our complementary triangle over here, this small one, that angle is phi minus 90, which says that FDH times cosine of phi minus 90 is the component of FDH that is acting perpendicular to the edge of the linkage EDB. Now we have a geometric relationship that we can establish between FBC and f sub dh, and that's coming from summing the moment around point E and setting it to 0. And we're going to go through each of these terms carefully because they're a little tricky to understand spatially. First, we have this component of FDH that is perpendicular to the linkage. It is going to create a moment that is going to want the linkage to rotate in a counterclockwise direction about point E with a magnitude of FDH a cosine phi minus 90 degrees and a lever arm of small a. That's our first term. The second term is a force B is acting downward, and it has a lever arm of 2a times the cosine of this angle theta. And the third force that creates a moment is force F sub BC, which is acting normal to B, and it wants to rotate clockwise around point B, and it has a lever arm of 2a times the sine of this angle theta. And we set those three terms to 0. In the second line of the calculation, we also know that FBC from figure 4 is equal to C cotangent theta, and that's the substitution done here. And we broke out these terms for FDH. We said FDH A of sine phi, because cosine of phi minus 90 degrees is just sine phi. And we have a minus B2A cosine theta, and then we have this term, minus C cotangent theta times 2A sine theta, and that, of course, equals 0. And then we do one more trick. We know that the cotangent of theta times the sine of theta is actually the cosine of theta. And by combining these two terms here, we get this simplified equation, f sub dh sine phi minus 2 times the sum of b plus c times cosine theta equals 0. And that is our second equation relating forces b and c, but of course it also has the term f sub dh. We can solve our two trigonometric equations relating b and c, and we obtain a relationship between f sub dh and angles theta and phi. So we rearrange the terms in this first equation to get an equation for f sub dh, rearrange the terms here to get 2 times b plus c equals w, combine the equation I'm circling with the second equation I'm circling, do a little algebra, and now we have a term for f sub dh equal to w, which is the full weight of the crate, times cosine of theta divided by sine of phi. Now the first thing we realize is this result is independent of distance d, so that's good. We know that theta is 60 degrees, that's good, but we don't know what phi is. We have to figure that part out, so we're going to keep going. Well, the first thing we can do is use the law of sines to obtain a relationship between theta and phi. So we take the triangle EDH and we draw it here on the bottom, and it has angles theta and phi in it. And per the law of cosines, sine of the angle phi is to L as sine of theta is to distance dh. That's this equation, and then rearrange the terms. We know that sine phi is then EH over DH times sine theta. And we can use the law of cosines to directly find the length of DH when theta equals 60 degrees. And using the law of cosines, we know that little a squared plus L squared minus 2AL times cosine is equal to DH squared. And if we just sub in numbers for A, L, and theta, we find that DH is 2.91 meters. Now W also can be calculated because it's 1,000 kilo mass and G is 9.81 meters per second squared. So W is converted now to 9.81 kilonewtons. And now we can use the equations obtained to solve for the force in each cylinder F sub dh. Now F sub dh before we showed it was equal to W times cosine theta divided by sine phi, but sine phi is equal to EH over dH times sine theta, so we can pop this term for sine phi into this equation here on the left for sine phi, and get that F dH equals W times length dH divided by length EH times the cotangent of theta. We know that W is 9.81 kilonewtons. We calculated before that dH was 2.91 meters, and the length of EH from this prior picture, the distance from E to H, is just length L. And we were told at the beginning of the problem that L was length 3.2 meters. And we know theta equals 60 degrees, so we know what cotangent of 60 degrees is. And you put it all together, and we have a simple equation now for F sub dH, and we find that it is 5.15 kilonewtons at an angle of theta equals 60 degrees. Now you might want to ask a simple question. Go back here. How does F sub dH relate to the angle theta? Does it get bigger or does it get smaller? And you can actually find out mathematically from this equation right here. As theta goes from 0 to 90 degrees, cosine theta goes from 1 to 0, which means by the time you're all the way at the top of the travel of this table, and theta is 90 degrees, FDH keeps getting smaller and smaller the higher the table gets. And FDH has its largest force when theta is a fairly small angle, so when this whole table is near the bottom of the travel, and element EDB is more parallel to the bed of the table. When the cylinder starts up early on, that's when it's going to have its largest force, because that's when theta is going to be smallest, and that's when cosine theta is going to be largest.